Hel- Hello, I'm Matt. I'm going to be giving a talk today on a paper I did with my co-authors, Burke and Shang-Hua Teng. I'd first like thanking the organizers for all the effort they put through, particularly through COVID, on getting everything working. And yeah, so this is going to talk about some fun game stuff. So as computer scientists, when we think of games, we look ahead. I do this as well at a personal level. And in general, like chess players do this. This is the common things with games. We're going to look ahead. When we look ahead at the game, something that we often notice is that the game results, the future moves are in some sort of simplified board state. Not every game, but for most games, the game gets simplified in some way as you go through it, and pieces get removed or pieces get added, and the board state eventually becomes simple. For example, let's just take a look at a late game position of Go. So for Go, you don't have to worry how it's played, but Go has a whole bunch of pieces you place on the board, and players take turns placing their color on the board, and sometimes get removed. However, in this case, most of these pieces can't be removed, and as such, we have these little small areas where you can place pieces, and as such, it results in a whole bunch of these small sub-games of Go. So really, it's like we have all this little small areas of games, and we're playing each of these games, we're making a move in one of these games exactly, and we're just alternating playing on these little small games. And this idea of like these small games that we're kind of playing at the same time, basically is what drives the idea of a disjunctive sum of games. So a disjunctive sum is, just more formally, on a turn, you pick some sort of game and you make a move on it, and the game ends when no more moves can be played on any given game. This is the main focus of combinatorial game theory research for three reasons, for pretty good reasons. Why? Well, I just explained one of them. Games naturally decompose. So, for example, if we take a look at this game of Cram, Cram's a very simple game. So in Cram, you just take players take turn just placing a domino on the board, and that's it. You can place domino either horizontally or vertically, and if you can't place domino, you lose. Very simple game. In this game, there's this kind of like four-like shape on it, and there's also these other small empty spaces. So really, it's like a sum of these five small games, the four plus the three small kind of lines. Right. So who can win the game? It depends on who wins on that sum of those five small games. Okay, so that's one reason that we really care about the disjunctive sum of games. But another reason is that it allows us to define generalizations. As computer scientists, hopefully we appreciate generalization is a very powerful tool. Let's just take a look at an example. Suppose I have some game put in the tree. You don't have to worry how it's played at all. Just assume there's some game, I do something on a tree. I add a node, delete a node, who knows? I'm doing something on a tree. Well, what's a very natural generalization of a tree? Well, a forest. So then what we can do is say whatever I'm doing on that tree, now I can instead select one of the trees and do that move on that. And that makes it my turn. Well, now we have the game play out in the forest. We just generalize the game. And that who wins that generalized game depends on who wins the disjunctive sum of games. So that's the second reason we care about the disjunctive sum. It lets us generalize. And finally, it allows us to explore game structures. So often in computer science, we're interested in who wins the game. This binary, you win or you lose. But that's not necessarily super interesting in practice, in the sense that I want to know, why is this move good, or how strong is it? How many points do I get if I get this move? How swingy is it? But we don't typically analyze that in at least theoretical computer science. So one of the strengths of combinatorial game theory is it lets us tell you why moves are good and how strong certain moves are. There's a terminology for this, there's mathematics for it. So you can say, well, this move is much stronger than this one, and you can give a quantified number to how much better it is. So there's a real strength in showing this, really not just this factual win or loss, but the intuition of why things are that you get with combinatorial game theory. So that's the three main reasons to study. So this has been studied for a long time. So a disjunctive sum of games of polynomial solvable games has been known to be piece-based hard for a very long time, since like 1981. However, the results have been limited in certain ways. So first of all, it's only applied to partisan games as opposed to ones impartial. Partisan game just means that the two players have different options. So for example, when you have chess, you have a white player and a black player, and the white player moves the white pieces, black player moves the black pieces, so they're not the same. It doesn't have to be you have a color, but just some way that the two players' moves aren't necessarily identical. Impartial games are just restricted to only having the same moves for both players, the same set of moves. So, so because of that, it's not, this result hasn't ever applied to an impartial game. Also, it was a sum of a polynomial number of games. Rather than, a small number of games, it took, well, we have these n, or the big O of n, simple, games. And then, because of this, they were able to construct things such that the sum of those n simple games are now intractable. So we want to improve on both the results to say, hey, can we get a sum of polynomial solvable impartial games and a constant number of them, and have that be piece-based solid? And the answer is yes, we're able to give that in this paper. Okay, so first I'm going to give some background to at least understand some of our stuff in more detail, and then I'll talk about our results. We can solve impartial games through something known as numbers, right? So in partisan games are much more complicated for analysis, but impartial games, fortunately, are much more simple. And all games have an associated number. So when I say game, I mean a specific position of a game, as in not, it's not like, oh, this one rule set, this one way of playing a game has something. It's just that this game, this position in this game has some sort of number for it. And then if we know the number for each of the games that we're playing, then we can say who wins the sum of games in polynomial time. So numbers are just elements of, basically they can be 0, star, *2, or star, whatever number, right? That's all numbers are. They're just some sort of, they're just that. And actually they're a generalization of winnability. So a game is losing if and only if its number is 0. If the number is not 0, then it's a winning game. So really, this is just a generalization of calculating who wins the game. Right? I just want to say, instead of saying who wins or who loses, I'm saying, well, I want more. Tell me if it loses, great. But also, if it wins, I want to know certain details which will help me understand who wins the sum of games. Okay, that's all I wanted to get through for this. Obviously, there's a lot more to this, but we don't have time to go through the full intricacies of how it works. Then now I want to talk a bit about geography, which is helpful for our result. So for a game called geography, it's played on a directed graph, and there's a token on some vertex. And then the players alternate turns, taking the token, moving it to another vertex, and deleting the vertex it came from. And the game ends if you can't move, where if you can't move, you lose. Okay, very, very simple graph game. And again, such a classical graph game. It's known to piece-based hard, even on planar bipartite graphs figure 3. In fact, this result is from 1980. It was in Papadimicio's book, and the first hardness result for geography that didn't have the planarity or bipartite property was actually in like 78, I believe. So yes, they're basically a very old game, one of the first piece-based hardness collections. But in this talk, we're going to focus on this game called Undirected Geography, right? Which is just the version of it played in an undirected graph. And surprisingly, this is actually in polynomial time. And the algorithm is actually really simple. Just say, hey, if the next player, or I should say, if the current player has a if the current player will win, if and only if the current vertex is an all maximum match. My current vertex being the one with the token on it, right? So that's easy to test actually. And yes, this is a simple algorithm, and you can in O n squared ish get who will win a game of undirected geography. So now I hopefully you can see where it's leading with undirected geography, and talking about this, we're going to be using that for results. And now let's talk about our results. So our contribution is the following. So first, if each vertex in undirected geography has degree no more than 3, then we can actually compute the number in polynomial time, right? So this is actually really pretty simple to show. It's not an interesting proof at all. It's simple and kind of obvious, but I can't really show it due to it requiring more knowledge about how numbers work. But if you understand how numbers work, it's not complicated at all. Then what I will show today is show, hey, even when you restrict to degree 4 for planar bipartite graphs, distinguishing between star and star 2 is piece-based complete, which therefore obviously gets us this long-standing result that's not been known about some partial games. And great in the specific thing for geography. But actually, we can actually extend this to any pair of numbers between, between any pair of numbers is actually piece-based complete. However, this requires obviously more knowledge about how numbers work, but it also involves some really more gross technical stuff. So this is, yeah. So this is not being included either. You can see that in the paper, but yeah, we'll be able to do that. And there's also an interesting extension to UNO, which I'll briefly talk about at a high level at the end of the talk. Okay, great. That being said, and now I want to talk about the reduction for at least the toy star 2 case, which isn't too hard to show. So now we have this directed graph here for a geography, current token on S, and we're going to reduce from it to a game of undirected geography, or specifically a sum of games. So I'm going to have one game that's just this very simple move where you pass, right? I'm going to call it star, right? It's just a one move where you can go and that's the end of the game. Just know that the number, that has the number star. Obviously, I can't explain why, but yes, that's what it has. And then that being said, the other graph here that we're summing with is what actually comes from the directed geography. So we're going to take that graph, and then for each vertex in that graph, we're going to add another vertex that's just adjacent to it. And for each edge, we're going to introduce an edge, a directed edge gadget, which will only let the players go through it in the correct way, and thus ensure the reduction works. Okay, and now I'm going to show you the edge gadget. So let's just say we have an edge SY, and we want to show how this works. So right now, just as a brief little trace through, I'm going to have us go from S to, I want to show that we go to S to Y. Great. So suppose you're on S right now. What if you go to S prime? Well, if you go to S prime, then if you go to S prime, that won't really work because you then your opponent can take the star, move, and then you just lose, right? Because you can't move. So that is. So then you got to go to A. And from A, well, if you go to A0, it's the same thing. So that doesn't work either. So we got to go to B. And from B, well, if you go to F, notice that then your opponent can take the star, and then you have to go to D, and then they go to D0 to win. So that doesn't work either. And then, therefore, you got to go to C, and from C, and you can't go to C0, so you got to go to D. From D, you can't go to D0. But then also you can't go to F because B is gone now. It's just the same sort of thing. So we got to go to Y. Great. And then backwards, we could trace to this. I'm not going to do it because of time, but just note, yeah, you can go and say, hey, if you go backwards, you're going to lose because no matter what you do, the other person has a response to it. Okay, and that basically is finished. And that basically completes the reduction. So what's the ramifications of this? Well, undirected geography winnability is easy, that is hard, obviously. But more importantly, it's just this result in general from partial games, because we've known it for a long time for partisan games, for a lot of them, but now you get for a small number of impartial games, in fact, 2 impartial games, which is very interesting. Second, it allows us to, it also is hard to sum 2 undirected geography positions into one single undirected geography position with the same number, which, in other words, if I give you 2 undirected graphs, you cannot make a third undirected graph that has the same number, which is not necessarily immediately obvious, but as a corollary with some of the stuff, extra stuff we can do in the paper, we could also make it so that we get this, right? It just follows out of everything else. So that's also interesting, right? That we can't even do this zero knowledge transformation or this zero knowledge summation. And finally, geography is so geography is used in a lot of things, and as such, it's always under geography, right? It's just a very simple graph game, and as such, it pops up in a lot of places. Speaking of which, let's talk about Uno. So there's a combinatorial game version of Uno called Uncooperative Uno. In this game, there's 2 hands of cards that are public. It's public. Everyone knows the hands of cards. And each card has a rank and a color. That's a pair of integers. And you can only play a card if the previous card shares a color or a rank, right? And then if you can't move, you lose. So just keep borrowing the public information, and you can't move, you lose, sort of thing. But beyond this, very simple, just Uno. I play red 5. Well, I'll play a blue 5. Well, I'll play a blue 7, right? Just a normal sort of thing. But now, do you notice anything about this? It's actually just this guy's game version of Undirected Geography, specifically one played in a bipartite graph. We have a one area that's just the hands, and then for each player for one partition, right? Partition for each hand, and then you say, great, the moves are going to correspond to what moves could be, what cards could be available, which we have. Okay, I play a 1. Well, then I play a red 1. Well, you can play a red 4 or whatever. We have all these options, and then it's just tracing through playing on geography until there's no moves left, right? Just the game mode. That means, hey, under this uncooperative Uno is in polynomial. That's not our result. That goes back to the original author, which was could actually either could say domain et al. They're going alphabetical, but I could also say Uno et al. There's actually 2 authors with the last name Uno in the paper, interestingly enough. Yeah. So anyways, that was what they showed on the paper. Great that they could reduce to undirected geography. So now we have this new game, Swap Uno, that we created just to show that something that we can do with our results. So suppose we have Uno, but each player has an additional card called Swap. And so once they play a swap, they swap their hands to their opponent, and they discard the swap out of that. So there's no more swapping after that. You can play swap, you swap, and then there's no more swapping. So what about this game? Well, it turns out, again, I can't say because we don't have the Nimber background, but it turns out that this is just equivalent to adding a star to the game. Okay. However, it's not. We can't just immediately apply our results because this is a reduction from Uno to undirected geography. And if we wanted hardness results, we'd have to reduce from undirected geography to Uno. And in general, you can't do that. But for our reduction, we actually can. We can reduce our reduction to Uno specifically, because fortunately it's bipartite, it's planar, and also certain other properties of it allow us to actually fit it into the rule set of Uno. And therefore, we also get that this swap Uno thing, and really Uno plus any number, any winning game actually, is actually piece-based hard. Great, and yes, that's it. Thank you so much for having me, and I think that is all.